All right, so might as well kick into this. Okay, let me just say one word about how I got involved in thinking about the complexity of all of this stuff, and it's still confusing me. When I worked at Sprint, I worked for the IP guys, and I got reorged to report up through Kansas City. If you folks know about Sprint, that's a culture shock. But the first thing my VP asked me was, he said, well, you know, I've been listening to these guys over at Rest and all the IP people, and they keep on saying IP is simpler than than circuit networking, and, you know, Sprint had all the kinds of circuit networking you'd want. And so he asked me, he said, hey, how come OpEx is higher on the IP platform than it is on either the Frame, Sonnet, or ATM platforms, if it's simpler? And, you know, I went, well, I'm not sure, and I'm still not sure. But that's what kind of launched me into trying to understand the complexity issues around all of these different kinds of networks and what they might have meant for designing them, and how that filters down into the OpEx CapEx equation, which we're also involved in right now. So that's kind of like where that came from, and that was a couple years back. And we had a panel at One Nanog over this, but it kind of defocused. And over the last couple of years, I think a lot of work has gone on, a lot of understanding of where and how this comes about has gone on, and how you might be able to use these concepts that seem pretty abstract to as design principles. So I think that's sort of the framework or the framing of all of this. So I'm just going to dive into this, and if there's anything that's not well explained here or that you're interested in or want to know more about, just let us know. Come up to the mic, whatever you want. So informal. So here's the agenda. A little bit about what we hope y'all will get out of this, what complexity is. That again is in and of itself is a big question. Why do we care is a big question. And then some examples of how this is really happening in real life and we see every day, and then a few summaries and some takeaways. And by the way, the skeleton of this talk was something that I built for SANOG, keynote I'm giving at SANOG at the end of the month. And the reason why I did this instead of something like how to build a route reflector is a couple-fold. One is that, you know, Philip Smith's going to be there, and all other sorts of people like that who can talk about that very eloquently all day long. But also because it's a little bit forward-looking. You know, what we're trying to do is establish sort of a science and engineering discipline that's based on a little bit more on rigorous principles than the way we do it now, or the way a lot of us do it now anyway. So that's where we're at. So this is what I've just been saying. My goal or our goal here is just to socialize this stuff with you folks, and, you know, have something else for you to think about when you're building and operating stuff. And again, always focus a little bit on the higher level principles, and then try to get it to the examples so that it'll be more concrete. Point out where the theory meets the application, because a lot of times, okay, we're in an engineering discipline, and, you know, the bottom line is that there's a bunch of physics and stuff under here, and I'm not sure that's going to be very interesting, but you can abstract back from that and find the higher level principles and see where those meet daily application, and that does turn out to be interesting. So, a few key takeaways. Oh, and if you want these slides for some unknown reason, that's where you could get them. Yeah.
You got a point to add.
Yep.
So we got to share the mic here. Yeah. But one of the things why this approach, which is kind of like a defining core principles of how these networks are really working successfully, is my experience in trying to cultivate new talent in the industry, whether it's, you know, with service providers out there or inside my own company today, is that if you go through and you teach them how to configure a box, how to configure BGP, things like that, certain things stick, but a lot of things get missed out. You still see certain principles being broken. You know, you see very complicated designs and things that run into scaling bottlenecks and things like that. But when you teach a principle-oriented approach, where you say, here's a core conceptual principle that you have, that it's going to be a guiding compass to how you build your networks, things that, and here are all these examples that we can draw upon, then that approach tends to get new engineering talent on a path that keeps them from digging themselves into holes. So that's one of the approaches we're trying to do here. We're just picking a couple of these principles out and trying to articulate them to a way where you can understand and maybe go back and teach your staff these core principles with it too. So this is why this is important, we feel, for the industry.
Well said. Well said. Yeah. the mathematics behind all this stuff will just be so boring, unless you happen to like math. Okay, so before we dive into all of this, this is the takeaway, all right? This is the key takeaway here. Things, nature, I think I have this here. Physics and people are going to push in the other direction towards more and more complexity no matter what you do. I mean, entropy is going to happen. So you have to be a little bit active. You have to be a little bit active in sort of pushing back or resisting that from happening, otherwise it will happen. And I guarantee you, having been in a carrier, it not only does it happen, it happens with all its possible permutations and consequences. So it's one of those things. Keep things simple. You'll always win if you do that. And we'll talk a little bit about what simple means. Oh, am I going backwards? Yeah. Okay. Magic point is like, it's not that robust. It's just not PowerPoint. Okay, that's what I just said. So what is this about? All right, so, we're talking about complexity, and, it's kind of this concept that people batter around, and there's groups of factions in the internet community who think things are complex or don't think things are complex. But there's a lot of, it's not really something that's well defined, and part of what I've been trying to do over the last couple of years is define that. So there's a lot of ways to do it, and I don't know how much, by the way, is that visible? Is that too small? Basically you got the classic computational complexity stuff where you're looking for upper bounds or lower bounds on some kind of static resource, memory, processor, space and time, and all of that stuff. That's not what I want to talk about. Anyway, this is like, how people always go, this thing has n squared because it's a mesh, but a lot of people don't know what it's order n squared, right? How many times have you heard somebody say that? It's order n squared. But how many people know what that really means? Okay, well, it means something like this. There's a curve that's bounded by n squared, and the complexity of the thing is always below that. There's a million other techniques, but these things are not what I want to talk about because they really deal with static properties, algorithmic static properties, or static properties, and what we're interested in is sort of what's called sometimes dynamical system theory, sometimes system theory, sometimes nonlinear systems theory, things like that. But basically what it does is it focuses on at a system level on the macroscopic properties of the system. And they're generally dynamic properties that only emerge at scale. And does anybody out there have a sort of an idea of what an emergent property is, or one that they like that they could share with folks? I'll do it if nobody else can. Okay, so has anybody ever seen one of those photographs that's made up of a mosaic of small photographs? Like I have this Darth Vader one, has a lot of Star Wars stuff in it. You stand back far enough, the property emerges that it's Darth Vader. But if you get close to it, you can't see that. That's an emergent property, and it's emerging at a scale. So the internet has all these properties that, when you have a small network, you don't see them, they emerge at scale. When things get big, these things start happening. And so this all applies to the internet from a systems perspective. And, it's what we're interested in typically is that, and from the operational perspective. And okay, so what kind of problems are interesting? I'll just name a few here, but we'll go on and talk about a whole bunch of other things we can look at. Well, the convergence behavior of BGPs in here. That seems to be interesting. Update propagation, that's related to, obviously, the convergence thing. The behavior of IGPs under congestion. And, it's something I've been calling PWE3 alarm multiplication. I'll talk about that a little bit more. But there are system level things that we can study this way that are not amenable to static algorithmic kinds of analyses. So why do we care? Anybody have an idea? I mean, why would you care? Wow, okay. Well, I tried to write down one sentence that explained why we care about this, and this is what I came up with. But basically, it costs you money. And complexity, it costs you money both in terms of how much it costs to buy equipment and how much it costs to operate it. And it's also involved in how you earn money, but it's really fundamental to that aspect of all of this. And I like using this one. Mike Odell, how many people know who Mike was or is? So Mike was the guy who was, well, Andrew does, of course. Mike was, tell me if this is right, Mike was probably the chief architect at UUNet during the years that it got huge, right? Is that fair? So Mike built a big network, a real big network. So he knows something about what you have to do to make a big network scale. And he stated this thing, which I don't know if I invented the term simplicity principle or somebody else did, but if anybody knows the answer to that, I don't know where that came from. And basically, he said that something like complexity is the primary mechanism that impedes scaling of your network, which means at the end of the day, that means that it's the primary driver of CapEx and OpEx, which is what we care about. And there's a lot of corollaries to this, like KISS, right? Keep it simple. Law of diminishing returns from economics is really another way of saying the same thing. Occam's razor, how many people know what that is? Occam's razor is basically, there's a lot of ways to say it, but basically it says, in the absence of overwhelming evidence to the contrary, the simplest thing has to be true, right? Something like that. I mean, there's a lot of ways to state that. So I was having Vince Fuller look at this, and this was what he said. And so I just wrote it down there. I just picked that out of the IM window. But basically, if you don't keep your design and implementation as simple as possible, and we'll talk about what simple as possible means because obviously that's key, it's going to wind up costing you more money, end of the day. And that's what this is about. So we're trying to import ideas from a more theoretical area of, networking, if you will. Some people call this networking, into the engineering community. So that's kind of what's going on here, and that's why this is a little bit different. Oh yeah, so here's the key question. So we got the simplicity principle here, and we got all the people out in the internet going, you got to keep things simple as possible, otherwise, it's the end of the world. But how simple as possible? Well, you got to watch out on that one, because this is another famous quote. Anybody know whose this one is? Yeah, Einstein. Good Einstein. Yeah, and I'll show you a curve later on that comes from the dynamical systems theory that actually this statement is sort of a more general way of describing that curve. Oops. Sorry about that. So, as I said, there's a close relationship between complexity, however you want to quantify complexity, and how much robustness you can get out of a system, and the system is your network. And the reason, and we'll see how these things are related. But what you need to remember is that complexity is the thing that drives robustness in your network. At the same time as it's driving the cost, it's driving good and bad features. So it's not quite as simple as saying, this thing is too complicated, or this is complex, or, as we've seen over the last year, especially when MPLS started coming around and people were thinking that was too complicated and so forth. It's not that simple, but it is possible to understand the relationships. So an easy example of this is multi-homing, right? That adds a lot of complexity to everything, right? Everything, your own network, the internet as a system, everything. Well, why do you do it? Why do you do multi-homing? It's to get more robustness, right? Because you want switch and you want vendor, switch, code, circuit, everything diversity, right? More robustness. So you do multi-homing, but you pay for that in complexity. Excuse me. So the key takeaway here is, unlike the big complexity wars of years ago, MPLS versus IP guys or whatever, the takeaway here of all of this stuff is don't walk away saying complexity is a bad thing. You have to push back on it, but you need some of it too. So the key is to understand where, how, why, and what effects on both OpEx and CapEx that you're dealing with are caused by this. So, hey Barry, jump in anytime. Or anybody who wants to have a question on any of this. So the question comes up is, where is all this stuff coming from? I mean, can we understand if we do something in our network, or if we design a protocol, or if we implement something, can we understand what effect it's going to have on the complexity that we measure in our networks by OpEx and CapEx, or any other measurement we want? Well, there are a ton of sources, and there's no way we could really go over this in an hour or 2 hours or a day or 2 weeks or probably, I don't know. In fact, I don't even understand it all myself. But the main one that I'd like to talk to you folks about is that the internet's a nonlinear system, and it has various response patterns, and certain principles and properties of nonlinear systems are applicable to the way we design. But we have to kind of import that stuff, and that's what we'll be talking about. So Sorry about this. It's like dry air or something. So recent work in this area, and there's a ton of recent work in this area, and I can point you guys at any amount of literature if you're interested and really bored. But the systems like the internet, and I'm not going to go into deeply to what like the internet means, but just say that they're large, nonlinear, highly designed systems. They have a property that's being termed robust yet fragile. And we'll see what that means. It seems kind of like a contradiction, right? It seems like if something was robust, it wouldn't be fragile. What this means is it becomes more robust to the events that it's designed to be robust to, and it becomes more fragile to unexpected events. Okay, so we'll take a look at that. The basic thing here is that all these results, if you distill all this down, what it says is that, a system is going to need some degree of complexity, and complexity here is meaning design, really. Design is a measure of complexity to achieve robustness, but it's going to do so at the cost of increasing sensitivity to what are hopefully rare events. So what you see is if you get on the wrong side of this, you see cascading catastrophic failures, and we see those all the time in networking, unfortunately. Or fortunately. So this is the thing that's important. The system's robustness is bounded. In other words, for a certain kind of design, there is a theoretical limit to the robustness you can get out of it. However you measure that, it's not really important how you measure it. But the complexity is not. So, and again, it doesn't matter how you measure it. And okay, so this is the one theoretical thing I'll give you, and then I'll get off that after this. It gives rise to something called the heavy tail distribution, and I'll have a picture of that on the next slide. But what does that mean? Well, you'll see the picture of the heavy tail. What it means is long tail distribution. But there's all kinds of interesting results around this, and the one that I thought was sort of interesting is this one. And it basically says that if you use this design rule, when you add a router, you add it to a more highly connected router than a less connected router. Then you'll get this distribution. Well, interestingly, a lot of current POP design produce just that effect. Like if you stick a router in your POP, generally you're going to connect it to your route reflector, right, which is the best connected box in your POP. So you're going to get this effect. So what does it mean? Well, okay, here's the curve. This is the only one that you're going to be subjected to. But basically what this says is, see if I can make this work. So the complexity is along the x-axis along the bottom. It's not bounded. It'll go forever. The robustness is bounded by some value, which for constrained problems, you can actually compute that with enough machinery, a ton of machinery, mathematical machinery. But if you look at this curve, if you're to the left of that point called P max, then adding complexity to your system is you're winning, right? Because you're becoming more robust and you're winning. If you get on the other side of that, you're in trouble because you get all the bad aspects of having a complex system, which we'll go through some of those later, but you don't win any robustness. So a lot of people think that multi-homing over a certain degree actually pushes you over to the other side of that. So there's a site on here. This is only for the really bored people right here. All right. So where does it all come from? Well, all right, so remember that all of this machinery is getting built with the idea that hopefully we'll be able to get some design rules out of this or some things that we can watch out for when we're building our networks. So it's not that we're trying to build a theoretical edifice for all of this, but these things turn out to be linked directly to daily life. So their amplification and their coupling, and we'll see what that is. So these are things that, amplification really says there are things that are going to emerge at large scale that you don't see at small scale, and that's because they're amplified. That's why we're calling it amplification. And the corollary is in a large network, even small things can wind up and do cause like huge events. Things that were small when your network was small can cause huge events. And then what this means in the more system theoretic way of talking about it is that if you had a function that, if you could imagine that the internet could be described by a function and it had some inputs and some outputs, things get amplified when the inputs are sort of decoupled from the outputs. In other words, small amount on the input causes huge on the output. You know, so they're somehow decoupled, and that's not a linear function. Trying not to bore you with this stuff. Trying to get to the examples. So the takeaway here is when your network gets bigger, as things scale up, even things that once looked extremely small and trivial can kind of turn out to be big. The trick is which things and how and when. So here's some examples. The canonical one that everybody talks about is the way that you get multiplication of updates across the mesh of the internet. And there's a really nice paper. I don't know how many people know Tim Griffin, but he wrote a really nice paper on this. And there's some sites at the end of these slides, so if you want to get them, or you can get them off my website, I have all this stuff. But so that's an amplification, right? You put in a few updates and you get out billions, or however millions. Okay, I talked about this earlier. This is something that's not quite been understood yet, but if I have a bunch of PEs or whatever I want to call it, my provider edge routers, and I'm terminating hundreds of thousands of pseudo wires on each one, and I have hundreds of these things all over the world, or thousands of them, and then at some point in my network I have a OC192, and that OC192 comes apart, and all of a sudden I broke some number of pseudo wires, which I don't know how many there are, or where the endpoints of them are, or anything like that. So now I have this alarms coming to me from all over the planet because these pseudo wires went away, but there actually was because there was this one event. Oh yeah, okay, so that's the point. So there's a takeaway in there, and it really means that when you have aggregated or mesh kind of structures in your network, you know, take a look at that. And by the way, organizations suffer the same exact phenomenon, so you might want to look at that in your own organizations too. Anyway, these things are sources of unanticipated amplification, and it happens all the time.
So here's another example of amplification that's probably a lot of people are probably looking at right now, is you get this hyped up word called deep packet inspection. Oh, let's do deep packet inspection stuff. Now, of course, I keep on asking people inside Cisco say, okay, we need deep packet inspection. I go, well, what do you mean? What's that mean? But what a lot of people define what that means is looking at a session and keeping state on it. And there's a whole slew of stuff, and you know, we're one of the vendors, one of the slew, but a whole bunch of vendors saying, oh yeah, we got a box that can take care of this. And this is where the amplification effect kicks into play. Because taking these things, how you terminate state and manage state in like a enterprise, an endpoint, you know, internet's end-to-end, I got a client, I got a server, I connect up on the endpoint. So if I'm not on the endpoints, and I'm taking state, that's one thing. But when I get into the middle of my network, amplification effect starts taking effect. And what happens, the whole science of your expected behavior of state on the endpoints, you got to throw all that out. Because as soon as you move it inside the network, inside your core backbone, and amplification forces take over, there's that world of state has never quite panned out. And we can point to, you know, Philip Smith is a good one to talk to, like over in Asia, where people tried to like put NAT boxes in the middle of whole big backbone architectures because we couldn't get IP addresses. They put all those NAT in there and had all these wild sort of things happen on networks because they're putting state in the middle of a amplification effect, and had all this unintended collateral incidents happen because of it. So this is another. I think this is another example put in there. Is as you look at it, you couldn't draw a one-to-one correlation and say, well, if this sort of state management worked well for scaling my web servers, I can take the same thing, repackage it, and call it deep packet inspection to take care of peer-to-peer networks and stick it inside a middle of a POP. And it should work, right? It should work. And then you stick it into your POP and you notice, wow, what's going on here? Why am I getting these strange calls from my customers who see these weird things happening on my network? You're scratching your head. And you trace it back to things that you never expected to happen because amplification effect happened with state.
Oh, so, you know, I was just thinking about this while Barry was talking. I said, well, why doesn't Moore's law solve this? You know, I mean, why doesn't somebody ask that? You know, just get some more memory and processor. Why doesn't that work? Anybody have any idea about that?
You don't upgrade your gear on Moore's law.
Well, that's true. That's probably even more true, which is that your equipment amortization cycles don't match Moore's law. Is that what you're saying, more or less? Yeah, but if they did, would it work? So that's even more true, because what you're saying is you couldn't even operationalize it if it worked, right? But if it did work, would that be enough? Why not? Why, I see you shaking your head. Why do you think it would not be enough?
Scanning mode will exceed all possible resources.
Exactly. Exactly. You have a nonlinear process that can diverge at any point. That's what you're really looking to prevent, is this divergent property. Because if you could keep things under Moore's law, you just ride Moore's law, and there's no problem. But there is a problem, and it's just, and these properties, amplification and coupling, we'll see in a second, are just properties. They're kind of physical properties of building networks at this scale. Go ahead. Oh, you know what? I made two mistakes. One, I forgot to ask you to stand up and state your name, and two, I didn't notice that I forgot to.
Charles Spurgeon. I like Barry's example because it talks about the security stuff that is so very popular, and we have this sort of ongoing conversation with security people who want these features. They see the enormous value of the features, and they're not responsible for the operation of the network. And one phrase that I keep using is, you're painting a bullseye on the infrastructure to try to accumulate all this scanning, all this state that can come from scanning attacks or whatever kinds of attacks in the equipment that has to actually move the packets. Until you point that out to them, that's not obvious. For
Right.
them, it's like you're, it's another line I use is like trying to take candy from a baby. But I mean, they have these features they really want, their users really want, and they can't understand why they shouldn't have them.
Well said. Hey, one thing. Hey, whoever's the AV people, can we get some more gain on that? Oh, okay. Thanks. Turn up the monitors or something.
Yeah, kind of add to that with, like, backbone people talking to security people. Like, you get the security person goes, "Oh, why can't I put a firewall on my peer endpoint?" And then you have to, this is why these principles come in. So this is another reinforcement point, because then people call me up and says, "Oh, Barry, can you help us explain to people here, this customer, because the backbone people and the security people are frightened." And the backbone people are not used to the working on the endpoints. They're used to working in the middle, right, of, the way you build robust backbones. And then the security people are used to working on endpoints, and it's a clash of two different worlds, two different principles of how to scale together. But if you had certain principles of understanding how, robust network designs have been built with IP, then, and both parties understood those principles, then people will say, "Oh, okay, now I understand why you can't put state at this point in the network. What can we do? Right? How can we achieve the goals living in the world that we live in?" Right.
Let's see. Let's see what's next here. Oh, yeah. Okay. The other thing is, one of the things I've been trying to learn myself and teach the people around me about is that the principles that guide how our network works when it gets large, all of this nonlinear systems dynamics and all that stuff, actually that's part of a physics, that's part of nature. And if you go out and start looking at this, you realize that there are all these kind of principles. You see this stuff coming up all over the place. So this is one of my favorites. So, Craig and Abba had this paper that showed, it could take factorial time for BGP to search, for the right path. It's a corner case, but it can happen, right? So you think that's bad? Well, it can get worse on amplification. What happened here was there was what's called resonant linear amplification, and basically the bridge was built with the right harmonics for the wind, and it just, in an amplification wave got set up in it and, blew it apart. You don't want your BGP to do that, but it happens in nature. I mean, this is exactly the same effect. Bad result, by the way. Wish we had two mics, it would be better.
Yeah. So you actually see this on the internet when you work the security space. I've been doing security the last 5 years, so I got to put the security analogies in. But you'll see these cases where if you put multi-home networks, right, in your multi-home condition, you're doing stateful firewalls and load balancing and things like this, and you'll get these DOS attacks that will knock down the BGP connection. So you start what you get called the DOS flap, right? And you'll get this harmonic setup where the DOS attack will steadily flap from one link, knock it down, state tables are overload, you'll fail over the other connection, and it's like it's a fire hose going back and forth whack one link, whack the other link, whack the other link, other link. And your service will be up and down and your variance all over the place. And we saw there's a couple of miscreants out there that have botnets that could craft these just right, where they are low level enough where they knock everything down, mess up your state tables, start flapping over without, and you think it's like a surge, it's a customer surge, but really what the guy's doing is messing with your site and causing a performance hit. And that's because they're timing the oscillation just right of knocking down state tables in BGP and the congestion collapse just right where it fails over. It just flats back and forth between the two different connections. So this is where we do see this sort of thing that do happen on network. BGP is one, security is another place that we see this happen.
I have a bunch of examples at the end. Yeah, so the point of this is that, there are physics here and they're useful for us, but not for them. But by the way, if you ever get there's a film of this, some guy's out there in a car, some idiot is out there in a car, gets out of his car, starts running away. It's an interesting film, but it's an interesting case, but it's just a case of the same phenomenon called amplification. So the other one that we were talking about is called coupling. So this one's also when things get larger, but one way of thinking of this is as things get larger, they exhibit increased interdependence. And this is kind of a physics thing. Why? Well, because the more events that simultaneously occur, if you just think if everything had a uniform probability distribution, then the more things you had simultaneously occurring, the larger the likelihood that two or more would interact. And Doyle and Willinger, if you ever want to read their paper, it's kind of interesting, but they just have some more fancy term for this called unforeseen feature interaction. Can be coupling, can be horizontal, so at the same layer, if you think about protocol layers, or between layers, so up and down the stack or across it. So what are the examples of this? Well, Van and Sally have a couple, the first ones, I think, and they were all about synchronization on control loops, things like routing updates, synchronized routing updates, and TCP, slow start synchronization. People know what that is? Is that so old that nobody knows what that is anymore? So the idea, nobody knows? If you don't know, raise your hand. How about that? That's so old, nobody even knows about it. Wow, okay, I'm old. So it means that coupling is kind of related to synchronization. And, we've seen this happen a couple times. Red, weighted red, various crypto techniques deal with injecting randomness to get robustness. Break this up. And the other important way is that ensuring locality of reference basically on everything, if you can do it. Oh, do you want to talk to this one, Barry? This was your picture.
Oh, you can. This is the standard.
Well, this is just a picture of what happens with red with an offer load. Do you have anything you want to say about this one? Okay. I think there's some more examples in here. Okay, how about ACLs? ACLs do a strange kind of coupling. Now, what a pain are ACLs, right? Well, there's a reason for it. It can be the case, they can do all kinds of different kind of coupling, but one of the ones that's most insidious, at least from the point of view of injecting complexity into your network, is that they can couple the actual application layer to the packet transport. In other words, well, here, think about extended ACLs and what they do. What you're doing is you're making forwarding decisions based on the application, so you got a direct coupling there. Pairing policy is another one. It's kind of an interesting, this one's a little bit more abstract, but we were thinking about examples this morning. I kind of like this one. It's basically you have these decisions made at whatever the layer the lawyers are on. Are they at 7 or what layer are they on? Wherever those guys are, but it's translated into a set of filters essentially and a set of cross connects and stuff like that. So what you have is you have this like completely compiled version into both the cross connects that you have, the ACLs you have, and all that stuff of that thing. So that's like a deep coupling that is not understood or represented anywhere, right? It just, you look at an ACL and you go, oh, okay, but it came from some lawyer dude somewhere. So what are the takeaways here? Well, obviously localizing impact of design or configuration changes, right? How many times have we seen that? That's the I typed no router ISIS route map, accidentally, and typed return and went, oh, hey, I don't have connectivity to the router anymore. Oh, what happened? Should have used the out-of-band port. Oh, and then the other thing is engineer for this human entropy thing. And this was, Barry and I were discussing this morning. This is kind of interesting. The Sprint example that we have here is a good one. talk through this one, okay? Let's see. I had to fight with Magic Point to get this to happen, so let's see if it really works.
Here we go.
Is that?
Yeah.
Is that readable?
So you can see this, like 2 nanohours ago, Ryan McDonald came and presented this. And what's interesting is the genesis of this, because the genesis of this applies directly to the principles what we're working on. So the problem set that we're working on is Sprint would have their customers get hit with a DOS attack. And a lot of Sprint's enterprise customers are like big pipe customers. And so the DOS attack, they couldn't get enough DOS oomph to fill up the link to knock down the customer. So you'd have a DOS walk. The attacker would then trace route and find out, okay, what's the next point upstream that I can hit to hit the attack? And of course, the next point upstream is the Sprint router. And it would hit the Sprint router, or they hit the service, the customer's router. So they take that, between the PE and CE link, that DMZ connection between you and your customer, they would hit that link. Or they hit the aggregation router and service provider. Or they hit the POP aggregation router. Or, so they would find some path in there. And so Sprint's kind of going through there, and they got this little working group and saying, okay, how can we solve this sort of thing? And factors came up. So we said, okay, can you do ACLs on the edge? And ACLs had all these things like the different couple-on effect and amplification effect and peer-in policy, and also when you become a firewall for your customer, and like in Sprint's case, you may have to get a lawyer to approve the ACL. But then you have also the human entropy. And human entropy is where, ACLs isn't, a lot of people say security, throw in an ACL really quick. But the problem with ACLs in an operational network environment is those things change. And when you got a big network and you got multiple points of entry, you got to maintain all of them simultaneously. And then as soon as you have them up there, you got other customers say, oh, let's add our ACLs in there. So you have conflict. You'd start having, ACL collision because policies start colliding together because it's policy all in one point. And it opens up the door for a lot of things, especially the human entropy effect where, once it's there, who's going to maintain it? Well, there's a cost. So we were looking for an answer that we can solve the problem of hitting the infrastructure links without ACLs, and it would be resistant to human entropy. And it just stumbled upon the technique that we came about, and it's working today, right, is to pick how you advertise things, right? So the DMZ addresses between Sprint and Sprint's customer are not advertised anymore, all right? So that if they're not advertised on the internet, I can't launch an attack to that destination. So the next thing is the infrastructure links. So the infrastructure links is a command that was put in IS that was put there for convergence, which basically in IS to IS for many different reasons, you don't need to have every single IP address in your RIB. Right? And of course, the bigger your RIB, the slower your convergence. So if you took all those point-to-point links on your infrastructure out of your RIB, then the convergence would be faster. Well, we realized, Ryan McDonald and we realized, hey, we can use the same command for security. Because if you use that command, those point-to-point address links are not advertised anymore. That means if a packet comes into Sprint, it goes on the border router on my edge. The border router edge says, well, I have no more specific path. So the aggregate router is advertising the aggregate out, but then once it gets into that first router, I don't have a more specific route. So I drop it. Goes down to 0, drops it in an ASIC. Yes? Yep. Can you use the mic and... There we go. There we go.
Can you hear me? Can you hear me? Ted's Amplified. I wanted to understand, when you say you're not advertising the routes, you're not advertising the /31s in that example, I guess, or you're not having any DNS entries for those routes?
They're both. So in Sprint's case, they're not advertising the /30/31s at all. And actually, they've actually started using unnumbered on those links.
What do you do for customers that typically use that address for their access to the internet? They NAT to that address.
They have special cases, but unnumbered, they would use the address that they're allocated to. So you can bind it to a different address, and the address would be going out. So NAT would work. You don't need to have that point-to-point link be the NATed address. You can use the address that's reachable to do that.
Okay.
So, you can set NAT up that way. It took about a year in Sprint's case to re-educate the customers, and there's a lot of customers that are still in transition at that point, right? So
the other Joel Krauska from Cisco. The other example you often see people arguing about this is using RFC 1918 in their core, and it would provide the same result, and I'm curious.
But what happened with RFC 1918 and with ACLs is it breaks PM2 path discovery and traceroute. See, that was the thing they didn't want to do, right? So you can traceroute through Sprint today. You know, TTL times out, and the router sends a packet back with the address of the OC192 link inside Sprint, right? PM2 path discovery works the same way. So you still get the TTL timeouts, and the router responds with a source address equal to that link address. Now, if you then took that source address into the link address and try to target it, the packet will go to the edge of Sprint's network, down 0 in an ASIC, because they put ASIC-based line cards on there, and ASIC-based line cards just drop at the full PPS rate of the ASIC when it goes down to 0. So, and now you apply the human entropy thing here. Now, what's it take to maintain this? Well, the provisioning guys with the policy on the edge is the biggest cost there. So it's the way you provision your customers. So that's the biggest cost, because that's the link out to the DMZ. The backbone guys, all they have to do, they don't have to worry about ACL or anything. All they have to do is make sure that that IS is configured in that way. So as long as IS is configured in the way it's supposed to be configured, right, which is a much easier problem to maintain the ACLs, then that makes the whole security systems, in this case this is one of the security systems to make the network more robust, it's more resistant to human entropy, because the network will change. When you add new things, like if I go in there and add a new section to my network, all I need to do is make sure my IS to IS configuration complies. I don't have to update any ACL on the edge. Right? So as my network grows, I'm less worried about maintaining control inside of an organization to make sure I get my new links in there to make sure I'm covered. Right? So I don't have to worry about that. So these are the effects of human entropy, how it affects in there. And this is where, when Dave was talking about organizational dynamics, in a big organization, all big organizations, you get this problem where left hand and right hand don't talk to each other. All big organizations are like that, right? And and they constantly change. So as soon as you get left hand and right hand talking to each other at one instance of time, organizational dynamics is going to pull that apart over time. So a year later, they're not talking to each other again, right? And so when you got these dynamics going on, these are the factors of human entropy. That's one of the things, organizational dynamics and human behavior affects human entropy. So you want to design a system for that. So this is an example of a system where human entropy was a major factor in there, trying to figure out how to solve a problem, looking at all the tools at hand, and come up with a creative way that's resistant to the human entropy effect. Right? So now somebody on Sprint on the West Coast can add a section to the network, and they comply to the way you plug a router in with the way they configure IS, and then they don't have to worry about updating Sprint on the East Coast because, you know, they have to update ACL policies or something, because there are no ACL policies to update. And if you want to see the details of this, Ryan's presentation is two nanogs ago, so that's all on tape and the materials are there.
So that's an example of an explicit decoupling, attempt to decouple policy from the actual maintenance of ACLs. And, you know, of course they win, because the ACLs can, you know, you can, however you want to measure the complexity in this number of lines or whatever you want to measure them in, that's not constant, where this is constant. Oh yeah, so the 5 nines example is kind of related to all of this. It's like, why is it hard? I mean, you know, a lot of people probably will say, well, no, it's not hard. Okay, not anymore. But, well, it turns out that there's a lot of literature and experience around that says basically 80% of the unscheduled outages are caused by people or process. And there's a site there. I like to use citations so that it doesn't look like I'm making up as much stuff as I really am. But what it says is that there's like only a 20% window in which to optimize component reliability, because, you know, basically like optimize your router, how good your router is, because no matter what you do, 80% of the time it's because somebody typed no router at PGP or something like that, you know. So and it doesn't matter how good your router is if you get that stuff happening. Well, so why though? Why is this? You know, I mean, that's the kind of question we're trying to ask, so we can understand what the principle is to avoid it, right? Well, because the way we increase component reliability generally is adding complexity. They become more complex. You have, you know, HSRP, you have whatever HA stuff you have, it's more complex. And remember that narrows the window even more. And you got to remember that, you know, we always add complexity to get more robustness. That's about the only tool we have. but it effectively continues to narrow the 20% window that you had. So the bottom line on this one, from the principal's perspective anyway, is that optimization frequently increases complexity, and that increases the likelihood that people and process errors are going to occur. And I was talking to VJ about this, and I was saying, it's really unbelievable. Can it really be the case that 80% of unscheduled outages are caused by people and process? That seems like, come on. Well, so he gives me this chart, right? And this is some data from 1902, right? 2002. And if you look across here, so this is tickets per day, right? Look across the bottom of that. When there's no tickets being, or when the low points in the tickets, those are weekends when nobody's around working. So, and this picture is well known, and not only that, this trend hasn't changed. It's still the same. He just happened to have that one lying around, so he gave me that one. But you get the idea. So if you go to the more theoretical stuff, which I have a tendency to do, so I always try to back off, but this has been characterized as a complexity robustness spiral in the technical dynamical systems literature, in which so you increase the complexity of something. Remember the curve? As you're going to the right, you're increasing the complexity, but the robustness is kind of, after a certain point, kind of goes down. Okay, so what happens is that means you're increasing the sensitivities to different things that are happening, right? So what do? Well, you put more complexity into the system to compensate for that, and you're in this spiral thing. And I'll give you, I think I have the well-known one here. Yeah, this one's courtesy Sean Duran, the graphic anyway. Actually, the name Ouroboros and all of this stuff, Sean gave me a little bit of history about it, but I got this picture, whatever the last year we did Nanog in Eugene was, I was looking for a good thing to put on the t-shirt, and they kind of did the complexity thing, but also did the Eugene thing, and it turns out this was a picture drawn by Robert Hunter, who was one of the lyricists for the Grateful Dead, so of course it links directly to Eugene immediately. And, but it's a complexity robustness spiral that he was complaining about. Again, so this happens in nature, right, which is they get more demand, they need larger halls, which means they need more equipment, bigger organizations, larger overhead, but then they need more gigs to support it. So that causes the fact that they need larger halls, more equipment, and so now they're in this spiral, and that's exactly what happened to them, until they had this mega thing that was traveling around. But that's a well-known one, I think. So, all right, so that's kind of those are the kind of principles that are out there for us to use right now in terms of thinking about how we're designing networks and building technologies. And so just reviewing this amplification thing, things can blow up big when things get large, and coupling, things get linked together in different ways that cause unanticipated and nonlinear, importantly, nonlinear effects. So some examples, well, we talked about a little bit about the multiplication of updates, BGP updates across the mesh. That's kind of a amplification example, and that was sort of, that's something that's unanticipated, right? I mean, because we didn't have a design principle that said, hey, well, if you build this really meshy thing and you start having you have this path vector algorithm, well, it might amplify these things. Or maybe Yakov thought of that, or whoever designed BGP, but linked state routing protocols have some. You get amplification when you have cascading failures due to the congestion problems you have when hellos start timing out and stuff like that. And then you have this horizontal coupling of the stability of the network to the congestion of the routing stability to the congestion of the network. Why should that be? We built inbound control plane. That's going to happen. Nope. Well, okay. So here's another one. Some of these are like really things that we're just working on right now, and I'm kind of telling people, hey, listen a little bit and kind of make sure you understand what you're doing when you're building this kind of technology. So OAM mapping is sort of this, anybody know what that is? Basically, okay, I have a pseudo wire, and the attachment circuit's ATM, and I got an AIS, right? And I want to send that AIS across my, my backbone network and dump it out on the other side. Well, now what I've done is I've coupled the alarm infrastructure on the ATM to my transport infrastructure, right? So that can have all kinds of consequences. I talked about this a little bit. We really haven't solved this one either. If I get lots and lots of pseudo wires going down that happen to be funneled through someplace in the network. By the way, if anybody has data on something on like pseudo wire aggregation or how they get aggregated in their network, I'd like to see it. I'm trying to find out if this really happens or not. But that's a case of amplification and vertical coupling. Oh, okay. Well, I want to carry L1 or L2 over my MPLS infrastructure. I got to map either the timing signals of the TDM timing signals or something like that onto the packet space. I just coupled the timing infrastructures, and you can get amplification there in the same way. Oh, I just put TDM over IP because that one seemed to have a really tight coupling between timing signals that are in the TDM network and the packet network, and we have to do all kinds of things to make that hold up. 3GPP, I have an awareness raising thing on this, but I'll wait until tomorrow or whenever that is for that one. But that does coupling of services to the transport. It's a vertical coupling thing. Oh, and then we have the whole thing about layering. Layering, I had a whole bunch of slides on this, but it was too much. So I'll just say that layering considered harmful. Why? Because it does vertical coupling. And you might say, what do you mean? It's sort of a basic abstraction mechanism that we use to build things, but if you kind of look at this, you could see that these things are vertically coupled in a serious way. Like, for example, if you had, let me give the canonical example. It's not exactly in this one, but if you had IP over HEM and you're running PNNI in your HEM infrastructure, which people did and people still do, and in fact, a lot of people think that should be the ASON routing protocol. What happened there was you coupled what are called, I don't know how you want to call this, you coupled the slopes of the response times of both of the algorithms together, and what happened is that causes oscillation. But you got a coupling of the convergence properties of, say you're running OSPF and PNNI, which is sort of a version, kind of a OSPF-like thing, right? So what really happened there in the most geeky form is that the slopes, response time slopes of those two algorithms got stuck together. And if they're sufficiently close, you can show pretty easily that it'll oscillate. So that's one reason why this is considered harmful. Another one is that over-optimization or over-layering is another way to build just all the kinds of complexity, because you're doing mapping between the layers of the abstraction at every layer, and so you get this piecewise coupling of these things that way. You got another one? Okay.
So another example that's hidden, I think a lot of people in this room, is you got this triple play and all these advanced services that people say, okay, let's stack on services on top of it. The thing we have to watch out for is this is layering in action. As you start stacking these things on, the characteristics of voice, the characteristic of streaming, the characteristic of plain old web traffic, the characteristics of peer-to-peer, these will collide with each other. And people who have been studying these traffic profiles and see them collide together kind of know they collide together. And this is the type of layering that you have to watch out for. So when you design your systems, you try to make it robust and resistant to the layering effects. Because some of these things you're going to want to stack all these services, and like the slide before this one where you talk all these new waves of services we're talking about. A lot of these in the standards communities are done in isolation from each other. So in other words, the guys working on TDM and circuits over pseudo wires, are not the guys doing the 3GPP and the IMS stuff, and so each of these are happening in isolation from each other. And then all of it is expected to all, come onto a converged IP network of the future and all work magically together, right? And so what we do know is whenever we've had the expectations like that, things will collide with each other unexpectedly. And this is a layering approach that we give a warning about.
All right, so what was the point of all of this? You're asking yourself. Well, I mean, the first rule of all of this stuff is that things really need to be kept simple, because if you don't, you'll buy yourself all of these properties, and you're going to get them anyway. Also, remember that complexity isn't inherently bad. It's not sort of like a war between the IP people and the MPLS people as it was characterized a couple years back. It's not really about that at all. It's that you're going to get this stuff, and we got to get design rules and design paradigms and engineering disciplines that are going to allow us to build networks with this kind of complexity efficiently. We just have to figure out how to do it. A lot of people think we already know how to do it. So, one thing that I think people ought to be doing is just when they're designing their network, thinking about this and going, oh, you know what, I'm not sure maybe, because a lot of times these are dynamic properties, so they're hard to figure out. It's difficult to figure out where this might happen because you can't see it unless it happens. It's dynamic. So, understand if you can and document the potential, right? So if you're making something really meshy, you can imagine that's going to be a place to look for this to happen. Or if you're doing something that has a large degree of aggregation, that might be a place where this could happen. Oh, yeah, okay. Yeah, and remembering that, when things scale up, the things that were small get big, and some things that were small get really big, and that can cause problems. Again, clearly understand where the coupling occurs, because that one also causes all kinds of unanticipated effects. And one way to do that is to try to localize design impacts, localize configuration impacts, things like that. And it can also occur, the same thing here can occur in the operational environment that you live in, and engineer for human entropy, which was the thing that Barry was describing. Oh yeah, and the final thing is that this is sort of a plug for the standards thing. I don't know how many people go to standards organizations, but there's a bunch of them you can go to. And these people are out there building these technologies that you have to live with every day, a lot of times without input from you folks. So I can't encourage you. I mean, there are literally hundreds, tens SDOs that have your destiny right now, and they're doing it without your input, unless you go. So these are some. So as you go to the right, I guess it's, to your right, these get less and less well-known acronyms, but you can get out there 10 or 15 long of those, and those are active SDOs building standards that vendors have to respond to in RFPs. So, you're going to see this stuff. And make your requirements known, and in those environments, because if you do, that'll force the vendors to build the stuff that you need. And I think that I think one of the problems that we have, at least in a lot of these areas, is that we don't get enough vendor participation. And so I'm encouraging you guys. Enough ISP or carrier participation. So I'm encouraging you guys to try to get out there and do a little bit of that if possible. I guess that's all. Questions, comments? So before you go, so this is a little bit different, right, for a nanog thing, but the idea behind this, and I just want to reiterate this, is that what's happening here is like we're in a very young discipline, and the engineering principles that we have are just coming to light because we haven't been around that long. The science part of it is also very primitive. The physics that are underlying this is in a very early state, nothing like what you would find for mechanical engineering or civil engineering or anything like that. So we don't have any discipline that's really analogous to that, but we need to get there if we want to continue to scale the way we are now. Go ahead. Sorry.
Joel Krauske from Cisco again. This is a little bit tangential, but I would say network management and the people managing the systems is a system unto itself, and you can add complexity by adding tools, by adding templates, by having extensive training, and that can in turn increase robustness as well. And that's that 80% problem. It's not a network design principle, but it's a network management principle. So.
Yeah. Okay. Well said. Others. So I'll ask a question then, right? So, Spencer, you going to go? I'll ask one while Spencer's getting up. So, do folks think that having more rigorous design and implementation discipline would ever make a difference in their operations or in the way they deploy, design, deploy, or operate their networks? Engineering discipline that was sort of like based on mathematical principles and things like that. Like if I was a mechanical engineer and I'm building a part, I have a sort of a discipline I go through to do that that I learned when I was in engineering school or whatever. No. Okay, Spencer, go ahead.
So you talked a little bit about complexity within a protocol layer and across protocol layers. One of the things I think I'm seeing is the same complexity over and over again in multiple protocol layers as you start to see people doing application level routing. One of the things we were talking about with multi-homing in the addressing workshop that I guess we were talking in Vienna, the IETF, not quite 2 years ago. A little bit was that people were talking about doing multi-homing and robustness at every layer of the protocol stack. And you know, if we pick one or two or three, that would be swell. But I mean, it's like all of them.
Yeah, it's a good point, and you're getting new ones underneath and above all the time, right? So underneath we might wind up having a global routing system based on Ethernet, right? On top, we have things like, well, truly. And on top, going up, there's this whole new idea of dynamically routing pseudo wires across multi-hop pseudo wires. So that would be a whole nother, that'd be a whole nother what's called layer network in some kinds of people's terminology. But basically, that's another network layer all of a sudden. So these things, I agree with you, these things are popping up all over the place, and they all have the same properties and same relationships, and we're not analyzing that at all. I'll give you an example. I was talking to some people about the pseudo-wire routing problem, right, the multi-hop pseudo-wire problem, and somebody just said, well, why can't we just dynamically route them with, run a protocol like OSPF on top of the multi-hop pseudo-wire thing? And it's a reasonable question because we do that. That's how we do routing. But the problem really is that then you'll have nested control loops with exactly the same slope of the response time algorithm, and that's going to cause instability in the network. So in a way, we don't we don't have a solution for that that's fully dynamic. Of course, you can do it statically, but that doesn't reach your goal.
Yeah, I don't know if I said Spencer Dawkins, but we went through this. We went through this previously with retransmission. I mean, the reason we do retransmission at the transport layer was because we used to do it at several different layers, and then you'd have these weird interactions where it's like my transport's giving up while my lower layers are still retransmitting, and things like that. And it's just like we're losing any kind of clean architecture we ever had, and all the functionalities going everywhere.
No argument.
Charles Spurgeon. As I was sitting here listening to you and listening to all the great anecdotes, I was wishing that we had a sort of way of codifying that kind of knowledge. You're talking about how we're very early, very young industry, and we don't really have any good, solid engineering, concepts like the mechanical engineers do and all that sort of thing. And perhaps one way to do that would be to think of the patterns people, the work they've been doing, where they try to define recurrent patterns in the kinds of work. You came out of Christopher Alexander's patterns in architecture, and then some object-oriented programmers picked it up as a way of describing recurrent patterns in object-oriented design.
I'm not familiar with it, but I'd like to get a look at it. Maybe you can tell me afterwards. Sir.
Okay.
Yeah, I mean, all of this, as I said earlier, all of this is really about an awareness-raising kind of thing where, all of us are going to move forward into whatever, however rigorous our discipline becomes. Maybe it won't be, because a lot of this stuff is pretty hard, to be honest with you. Understanding the dynamic properties of the network, it can be difficult. But I still think that there's a science underneath it, and that science will allow us to build better, cheaper, faster, or pick two, networks, and I think it's because there are patterns there. We just don't understand them yet.
But building on what you're saying there, if there's anybody here in the room or eventually watching the tape interested in this codification of this sort of work, using the premises, early days, pop a note to Dave and I, because Dave and I were, we'll talk about this morning, trying to get more like-minded people working together on this. So just pop it in those, and maybe we'll have like a subteam of Nanog. Nanog gives us a forum where we can actually try out analogies, paradigms, principles through tutorials and talks and things like that. So we actually have a forum, and we can go off as a group off to the side and start thinking through these sort of things. So just pop us a note, and then we can form some sort of little working group team to exchange ideas with each other.
Part of the idea is actually to be able to have better conversations with people like the security people, because you can't remember all of this stuff while you're in the discussion, and be able, to point to it and say, look, here's the pattern that I want to discuss. Here's a quick description of the pattern, its contents, and its application that might apply to this conversation we're having, and it would help structure that kind of thing. Well,
it's funny, in another flavor of this talk that I gave over last summer, 30% of the talk was just on the point of why you can't do stateful inspection at a point in the middle of the network where the principles of Paul Baran rule, right? And then certain people, how many people here know who Paul Baran is? Right. So now there's an issue there, because actually everybody uses network and robustness topologies and methodologies that Paul Baran was one of the pioneers that came up with. The whole principle that we have every node making its own decision of how to forward a packet, and using that as a robustness model is one of the principles that Paul Baran was one of the first guys to espouse. The idea that, the IP was created for surviving the nuclear war. He had a contract to do that years and years ago. But that Paul Baran principle that we use today, so many people don't realize that's a core principle. So actually that's a body of academic science that we can draw from, that we can use people and walk them through that. So there's like 30% of the talk that walks people through, here's how this works. And it's interesting inside my own company, I'm doing this all the time, because people are acquiring these products and saying, oh, this is going to be a great product, we're going to put it everywhere. I'm going like, no, you don't understand. It doesn't work everywhere. And they look at me strange and says, oh, you're being difficult. You're not being a team player. You get this, Barry's not being a team player, he's against our product. I'm going like, no, you don't, there's certain principles that apply. If you go out there and you apply this and you go talk to a customer and try to push this particular idea, they're going to throw you out. If they, they either get two reactions. Either they know what's really going on and they're going to see it as like, this doesn't fit for us, and they throw you out. Or what's even more scary is they go, oh wow, that's a great idea, let's put it inside of our network. And then we have things collapse, right? Yeah. So anyways, send a note or talk to us off to the side, and that's something that we can do. Of having like people who are interested in this area, we can work together and kind of codify and figure out how to present these sort of materials to our fellow colleagues and peers out there in the industry.
There's another thing that you made me think of is that you could catalog. There's a lot of techniques that we can use to that we do use, that we haven't really cataloged, as techniques for doing things like, I don't know. I was talking to somebody the other day, and we were talking about the kind of low-pass filters that we use in the internet to stop things from, stop amplification. Like, for example, if you see a fault directly connected to you, then you alarm for it. But if somebody else tells you about the fault, you don't. So that's sort of a low-pass filter that has a pretty decent dampening effect on some things anyway. Anyone else? Go ahead.
You describe randomness as in red, and it's done in protocol implementations a bit as well.
Mm-hmm.
Is analysis of increasing that randomness? See if it has a value especially on layered similar protocols.
I haven't done that, but I'm sure there's plenty of work in that area because red is so well studied, right? I just I'm just not really knowledgeable. I'm sure somebody in here is, though. Too bad Curtis isn't here. He's a wizard of red. He knows everything about it.
What percentage of network architects have engineering degrees?
Do you know the answer?
No.
Not very many. What is that? Can you translate that into English, Andrew? What does that mean?
A couple years ago, pilots did at this point. Very.
But is it important? That's not a. That's not a rhetorical question. I don't know that. I don't know the effect. What would you measure? See, this is what I'm trying to get people to do. Okay, is it important? Well, how do you figure out if it's important? You got to measure something somewhere, right? And then you have to have a framework to stick those measurements in. So.
An interest in the academic
Please,
Hi, Travis Marlowe.
Travis.
This is more of a comment really than a question, but it speaks to what he just said about having engineering degrees and when I came into this particular seminar, I wasn't ready for this. You know,
Yeah.
I was more or less ready for a 1, 2,
Build-
3 design guide.
build your
right,
route
that
reflector,
You
yeah.
get in the books, and I'm one of those people that, you know, I'm not formally schooled in regular engineering principles like a lot of people are. So all these concepts, while cerebrally I knew they were there, I knew they were in the background, they had to be, I didn't know how to apply them.
So was this helpful at all for that?
It's helpful if it goes somewhere, you know, past this part. When you were talking about the codification of this type of thing into something meaningful for us, you know.
Got to get to I think, let me see if I can paraphrase what you're saying. Okay, the theory's all fine, right? I mean, you know, and if you're really bored, you know, nothing else to do, you know, it's like, okay. But really what you want is you want to be able to compile it into rules that you could say, oh, if I'm going to build thing X, this is one way of doing it, and it has these kind of properties, and I can actually apply that to a real-life situation, right?
Right, I definitely need it on that level, but at the same point, I also need to understand the mathematical ins and outs of it also, so that when that security person comes to me, I can actually explain this and look real smart to them, you know, and show them why they're wrong.
Okay, so I think what you're saying, and please correct me if I'm wrong here, is that both ends of this need to be expanded in some ways.
Right. I
Okay.
think that because, I mean, you just went through a whole bunch of formulas and everything that already exist. We're
Yeah.
just not using them today for our industry.
Right. We don't have that kind of discipline yet.
Right.
Yeah.
So write a book and also, you know, buy it.
No, I'll tell you my thing. Every time somebody asks me to write a book, I say this. I want to have had written a book. It's a great accomplishment. I just don't want to do it. You know how much work that is? I just want to have had done it. Go, Spencer.
So you're talking about the layer 7 plus stuff, which I don't remember the protocol order after that. Which one is it? 8 is finance and 9 is legal, or
I had that heavy shirt, you know.
Yeah, I
lost it.
don't have the shirt.
I just said 7 plus because I couldn't.
Yeah.
I didn't have better granularity than that.
And I think one of the problems we're dealing with is that those higher, that the 7 plus layer stuff kind of trumps everything else right now because we haven't convinced people that the physics is real. You know, we've been able to apply a few heuristics where, you know, it's like, you know, the things that have killed us in the past we've stopped doing, but we don't know how far we are from the next thing that'll kill us. You know, and I think that's you know, it's, you know, I've heard about people who had serious conversations about what would happen if you could only speed up the speed of light by about 5%. You know, and the good effect that would have on your products. Okay, but people don't have conversations like that because you just can't do it. You know, and you're talking about a problem. You're talking about problems where we haven't hit the physics hard enough to really bounce off yet.
Right.
You know, yeah, you know, we're not, you know, Moore's law hasn't saved us, but Moore's law plus a few heuristics has. You know, and we just don't know how far we are from the wall. I think, you know, is one of the critical things.
Yeah, so it's true. I mean, when some of this stuff started, I started talking to some people around the internet, and I'm saying, you know, hey, academic types, and I said, you know, ask us similar questions, and what I mean, from the survey I took, I thought what I could say. I'll give it to you in a second. What I could say is that a lot of these people were concerned that there is such a barrier and that we're closer to it than we think. But on the other hand, you know, things still work right now, and so you got to kind of find the middle ground there. And that's why I was trying to decouple the complexity thing from technology. Really, you know, it's not the IP versus MPLS guys because they both have complexity. So that you got to learn. We got to learn what the principles are and how to build things around it because we're going to get it.
I think one of the advantages we got having a group of like-minded people based around a nano community go off and work more on this is that we got a lot of researchers out there. Some of them actually come to Nanolog to actually find things to work on, right? So there's a body of experts out there in the academia looking to figure out these things. But a lot of them are scratching their head, okay, what is a good juicy problem that has operational relevance? They want to do something that's really meaningful to the community, right? So this is where we have a good opportunity here as we come up with these questions and we're trying to codify this stuff, and we scratch our head. Immediately as we start scratching our head, there's something we don't know enough about. Okay, let's get the word out to researchers, and there you go. At the same time, you have operators out there, and there's a lot of operators out there looking for university people to go figure out some of these problems. Saying, well, come to me with a meaningful project that's going to help me out, and I'll give you data sets so you can get relevant data off my network and stuff like that. So you got this synergy that could happen here, and this effort could be a catalyst to help more of it happen. So, any questions or comments?
That's it. I'll just follow up on that.
Yeah.
So I just want to follow up on that one. So this guy I work with at Caltech, a guy called John Doyle, he told me, I read his work and I said, hey, this, we're in the internet thing, and this looks like something that we could, that was pretty far out. It was you can see in the references to this thing, some of that stuff's pretty far out because, as I said, the physics is young, the whole discipline is young, and all of a sudden we come up with an application. We got an application for something like that early on because the network got big quickly. So it had some historical anomalies that way. But what the guy told me, to your point about people wanting to get involved in this, is what the guy told me is, he had two goals left in his career because he's a professor at Caltech. He said two things. He wanted to be mentioned in an RFC, and he wanted to play in the NBA. And so I handled the first one, but I couldn't do anything about the second one. And anyway, the guy turned 50, and so Anyway, more. Well, while people are thinking about whether or not they want to answer a question, it'd really be good for people to, I don't know what kind of feedback mechanism we have other than the web. I know we might have some cards or something, but and I know there's a form on the web, but it'd really be good to give honest feedback, your honest feedback. I mean, it could have been a waste of time, I'm not sure. It is sort of early on, and it is sort of like theory stuff, and it is not maybe exactly linked to what you're doing every day. So the question really for folks like you to answer is whether or not Nanolog should be getting involved in any of this stuff or not. We could, there's plenty of venues to do this kind of work, but if we don't bring it here, it'll turn out, it won't get tailored to our needs, because I'm not sure that I can represent each and every one of you when I'm, wherever I am, so what I'd rather have happen is sort of a more participatory environment where the service providers are driving, because that way we'll get, that's why I said that about the standards too, by the way. I think the service providers really ought to be driving, not, obviously we're going to consume the service providers because we need to, but we can also drive. So this is another area where I think it would be helpful, because it would help direct research, because right now it's a pretty big field, and people of course are interested in the internet because there's cash associated with it, and makes people come and be interested, but it's very theoretical research for the most part right now. All right, any others, or we'll let you go? Oh yeah, go ahead. Yeah, go ahead, please.
Andrew here. You mentioned about about RED. I'm kind of interested on the congestion end. Are you folks, in your experience, you guys are seeing a lot of ECN being implemented? What I mean by the explicit congestion notification on the router end? Because I know at least on the
implemented or deployed?
Deployed. Which kind of takes a role of back pressure or kind of sender receive, does it on the router end, which
I personally haven't seen a lot of it deployed. I think it's more of a audience because it's a deployment matter. I mean, there's a lot of implementation work that's been done, but deployment is one of my wake-up calls that happened last year was April of last year, and this relates to the explicit notification, congestion notification, the ECN work, is April last year we had a Uniras announced a TCP reset vulnerability. And in talking like with the top 15 providers of the world, we realized that there's this thing called BGP Graceful Restart that is a very powerful security resistance tool for BGP. And so we asked the 15 providers where you are for deploying HA. And they all said, well, we have no plans of doing HA. So even though you had the two major vendors out there both had it in operational code, and all 15 providers had it in their operational code that were deployed, so it wasn't an issue of, is it in my image? It was in an image. It was not only in the images and deployed images on their active backbone running operationally, but this was a feature that a lot of people talked about and worked very hard with, but the operators just didn't have any business justification to get it deployed. And I think ECN it may be caught up in one of those cases. There's a slide that Dave and I were looking at where the reality, and with a lot of people here who work in operations work, you got what we call this work queue, where everybody wants to do the right thing, but the right thing gets pushed to the bottom of your work queue. And at the top of your work queue is enhanced revenue, new revenue, optimizing revenue, all driven by the product managers that you work with, and they're driving this stuff. And the stuff that you would really like to do because it's best common practices are the right thing to do are there, but at the bottom of the list you never get to them. Because every time you claw off one new revenue stream, there's another one that fills a gap, and you're constantly up there with everybody running lean, mean, you never get off the top couple of items on your list, all of it revolves around new revenue.
Because I know Sally and Van are kind of also, Sally has actually a paper on it, probably goes as far as 1999, which talks about ECN, and even though you can have implemented today, you can implement that on your routers. I mean, if the upstream or downstream they don't have that implemented, it kind of goes back to TCP Reno.
It goes back. It needs to be done. And then now, if you can come up with a business case where a product manager at a telecommunications company will realize how they can make more money off of it, then it'll get pushed to the top of the work queue. Right? I think that's kind of like, so you see a lot of heads nodding up and down here, and they're going like, yeah, we know that. So I think that's where we're at with ECN as a deployment factor. Yes, got another.
Yeah, Daryl Newcomb. Things like ECN, I mean, things that are fairly good ideas. I mean, that's one of the things that we can get, I think, from the research community is that to prove that they actually would be valid. There's a lot of conflicting data on ECN. Is it applicable? Is it actually successful? There's been some mock-up, lab-type environments that it was deployed fully, and it's actually been negative results, a number of different times. So I think, that type of thing is really valuable. I think for, to make the decision about where does it fit in the work queue. Is it really valuable? This specific technology, should it really get deployed or not? And making that estimate today is really hard.
Mm-hmm. Well, I think for something like ECN, if you prove that it works within a large system through research, then what you got to do for the product manager at a service provider is show how it will enhance their triple play options. Within their own, that's within their span of control for their video on demand and the voice over IP services that they offer. Because then they would say, okay, so this will be a differential with the competition if we deploy it in our network versus them. So that's where, even when we have the data, we still need to find here's the revenue plays in there, because otherwise you never get down to the bottom of the work queue. It's always at the top. Yes.
Just a comment on the ECN thing. So, according from your own presentation, ECN is one of those things that can severely amplify congestion, and that falls into some of the layering issues that Dave was talking about, and not repeat congestion control at several different layers. So it would appear to me that, at least from some of the principles that you try to talk, that ECN is kind of added complexity and it's unclear what's the provable gain. So probably what you're presenting here could let us decide if ECN is, but what the data you presented would actually point out that ECN would be extra complexity at no cost, at no value.
Yeah, so to kind of paraphrase again, it would be like, Pedro, it would be like saying, you could peg where it was on that curve, and it was past the max. You're over in the adding stuff that really doesn't buy you anything region. And the real challenge, is how to quantify that. So you could actually collect some data, make some measurements, and just say, okay, here's where I am on this curve based on this data. But the problem is we don't have the machinery yet at any level, including the physics dudes, to do that. I mean, a lot of this stuff gets reverse engineered because the forward engineering problem at the physics level about this is so hard. It's a gigantic dynamic system that has methodologies to analyze it are just being invented right now. So, well said, but the poor reality of it is that to get from these kind of principles to answering that question based on some input data that we might have collected is a couple years out at least right now.
That's even if you can define the system that you're attempting to.
Yeah, exactly. Going. It's too bad there's not like a beer and gear now, because then we could have a really good reason for getting out of here. All right, well, I guess that's it then. Thank you all very much.